Hello and welcome back to a series I've titled Under the Hood, where we analyze complex computer science topics and see how they work under the hood. Today's topic is hash maps. So before we start, we have to talk about the types of maps. And there are generally two types of maps that are used within programming languages, a hash map and a black-red tree map. Today we'll be talking about hash maps, and in a future video we'll go over black-red tree maps. And if you want some examples of what these are in C++, a hash map is unordered map, and a black-red tree map is just map. So this is code in C++ that initializes a map, gives it three keys, and then gets one of those keys. So first thing we do is we initialize the map in a key-value pair. So we have a string as the key and an int as the value. Next, for three values, banana, apple, and orange, we put those as the keys and we set the values to 100, 10, and 1 respectively. Next, we get map at position apple, which will print out 10 because in the middle we set apple to 10. So some things about hash maps before we start is insertion and deletion are in average case O of 1, basically meaning instant. And at worst, it can go up to O of n. We'll go over why that is later. And they also cannot contain duplicate values, which we'll also go over later. So here we have the code again. So what happens here is we have the three values, banana, apple, and orange. And let's keep these three as little values here on the left. And then the map will create a sort of table. And the table is basically an array. So here we have an array of 10 values, and each of them is initialized to null. So in order to, well, the computer doesn't really know banana, apple, and orange. It's not a pointer, it's just a bunch of text. So what we need to do for a map is we need to convert banana, apple, and orange to an index, so to map them to a value. So we do that. In order to do that, we use a hash function. So here we have a hash function that I custom made. It's a really bad one, but it will help explain it. What it does is it adds all the ASCII values together and then modulo 10 to get the last digit. So banana, you add up all the letters, B, A, N, A, N, and A, you get 577. The last digit is 7, so we'll take that. Same with apple and orange. So banana is 7, so it gets put into the 7th index. Apple is 8, it gets put in the 8th index. Orange is 4, so it gets put in the 4th index. And as they're stored as key value pairs. So orange will be stored as orange, comma, 1. Or as you'll see later in a struct or a class or something like that. So this is why maps cannot have duplicate values, because if you put another banana in there, well, you add up all the ASCII values, it gives you 577, you take the last digit at 7, but there's already an index there, and it already has banana. So it can't have duplicate values. All it'll do is override the value. So if I put banana something to 1,000, it'd override banana to 1,000. This is also why insertion and deletion is O of 1, because when I put banana in, all it needs to do is run the function. And usually it's not this add all letters, but the function will usually be O of 1, so really instant, and then it'll put the value into the index of the array, which is also instant or near instant. So what another thing that maps will do is, or you might see a problem here, which is, well, sometimes the hash can give the same value because we only have 10 values. So if I put hundreds and hundreds of food items, there's bound to be some conflictions. So here, what I added chat. So we're adding chat and putting it as a value of 100. But as you can see, it shares the same hash value as orange. So we put all those through. So what the map will do is it'll create a linked list in the array position so orange will be mapped to 1, and then chat, and then it'll have a linked list pointer that has chat as 1,000. So this is why worst case is O of n, because if you have so many conflictions that the linked list is very long, it'll be O of n however long that linked list is. A cool way that maps will combat this sort of is that if it's noticing that linked list is getting very long, it will extend the amount of indices possible. So from 10 to say 20, and then if 20 gets too big, then 20 to 40. So that can also introduce O of n runtime. And another thing is if, like, as you can see now, there are, what, 7 null values. That's a lot of memory being wasted. Now it might not seem like so much, but when you have thousands of values, a lot of places with null would seem very wasteful. So what it will do is it will cut down on, if it sees that there are lots of nulls, it will cut down. Instead of growing the index, it'll shrink it. So from 10 to 5 or 20 to 10. So you might be asking also, why use maps? Well, hash maps are useful for when you're accessing a lot of data, like in a database. So if you were to use an array, you'd have to loop through each value until you get to the value, right? So that would take O of n time at the very worst, where a hash map, on average time, it'd be O of 1, so it'd be very instant, and it would help for accessing data. So now we're going to go and write our own HashMap implementation in C. So here I have a basic structure of the way we're going to implement this. So I've already imported all the necessary libraries, and we have 2 types for key and value. So the base struct we'll be using is the HashMap, where we have a list of node items. And then each of those nodes has a key value pair along with the next node in the linked list. So I've also written a create hash map where we allocate the memory size for a hash map, and then we allocate the array size for the nodes. And we use calloc specifically here to set them all to null, so we can check later to see if they are null. And this is also a hash function that adds up all the characters of a string, their ASCII values, and modulos it by 10. And these are the 2 functions that we will be implementing, put and get. So I've already created the structure for how we're going to do this. We're going to do basically what we did in the previous section, where we're going to add banana, orange, apple, and chat, and see if all of them work with get. So first step for put would be to sort of initialize or get the hash value first of all. So let's say int hash value. So we're going to hash the key, and that gives us the index in the array, which we'll be using. So next we'll have to create the node using malloc. And then we'll have to create the pair too, along also using malloc. And then set the pair's key, and then set the pair's value. So now what we need to do is just set the new node's value to the pair, and then the new node's next to null, just because later when we loop through the array, we need to check that. So for put, we have 2 possible outcomes, at least when we're checking the value at the hash value, or the array index at hash value. The first possibility is that there's no previous value there, so all we have to do is just set the key or that place there to the new node. So that's an easy condition to do. All we have to do is just get the item's value at that position, check if it's null. Again, this is why we use calloc, to be able to check null. And then just set that value to the new node. So that's easy. The hard part is where we have to use the else. So what we need to do is we need to write a sort of code to get or to put a value at the end of a linked list. So this is pretty simple. We can just go ahead and current.next does not equal null. then we just set current equal to current.next. And then when next is null, we know that we've reached the final element, so then we can say current.next is new node. So this is a basic put function. One other thing that we have to do really quickly before we move on is that we have to handle the same value. So if I put banana in once and then I put banana in twice, so we'll use string compare, and we'll check if the value's key is equal to the key that we have already. So key is the key we're putting in, and current.value that key is each value's linked list key. So if they're the same, or we have to put equals 0. If they're the same, then we can set the value to new value up there, and then we free new nodes. We have to free the new node's value first, and then free new node dot next. And then actually, well, because we're not using the new node, all we did is just reused the a node already in there, and then we can just blank return because we're done. So that's a basic put function. Now we have to put the get function. Now this return 5 is just for debugging purposes. So same thing as before, where we have to get the hash value. Then some little blanket statements before we start is that we need to see if the value at that position is null. If so, we can just return null. And then if map.items at equals null, so this will check to see if a value is alone. So sort of like Apple in our previous example, where Apple did not have any conflicts, so it would be alone. So that's why we're checking for this. Then we can just return the value. So now anything we do onwards will be for if there are conflicts. So looping through the array and checking for conflicts. So we can write our node. We're going to do the same thing where we're going to loop over. And then we're going to do while node does not equal null. So if we compare the strings, and we see that they're equal to each other, we know that we've gotten the right thing. And then otherwise we can just keep on going. And then if we go through each of the nodes in the linked list and we cannot find it there, then we can just return null because we haven't found it. So let's go ahead and run this, see if it works. Okay. 1 second here. We need to do pair here. So yeah. So we set banana to 100, orange to 1, apple to 10, and chat to 1,000, and we get all those values back. So this is a basic implementation of a hash map. We're not implementing a real hash. This is just an example hash. We're not resizing or shrinking it down if there are too many linked lists, but this should be enough to get you sort of comfortable in knowing how a hash map works. And yeah, that's how hash maps really work under the hood.